Intuition Uncovered, investing for your future.
The following video is going to address pH calculations. So I'll cover calculations of strong and weak acids with respect to their pH, and then using Ka and Kw in pH calculations of acids and bases, and of course expressions for Ka, pKa, and how that relates to the acidity or alkalinity, pH, of various solutions and examples. So we've looked already at strong and weak acids and understood the difference between them, what partially dissociates, what completely dissociates, the level of dissociation being a reflection of how many H+ ions there'd be in the solution, and of course how pH is related to the concentration of those H+ ions in a solution. Now, Ka expression, we've looked at in a previous video. pH, the equation for this is minus log to the base 10 of H+ concentration, that's what the square brackets are. pKa is, as the pH is the P of the H+, we also have P of the Ka. So if you know the Ka value, we can do minus log to the base 10 of that Ka value and we'd have pKa. So H+ concentration, the bigger that number gets, the smaller the pH. In the same respect, the bigger the Ka, the smaller the pKa. Now, the bigger the dissociation in the acid, i.e. strong acids with a big number for the Ka, will have a small pKa. I hope you're following this. So a big Ka, strong acids, therefore smaller pKa. Strong acids have a high H+ concentration, therefore a low pH number. Now, ethanoic acid, a weak acid, small Ka would therefore be a larger pKa. Small concentration of H+ ions because of the small dissociation of the carboxylic acids, in this case the weak acids. It will therefore make the Ka a small number, but the pH will also be higher than, say, for a stronger acid. Now, what's worth noting though, although I've said stronger acids dissociate more, weaker acids dissociate less, generally, yes, it's possible. You'll have two solutions. If they have the same concentration, then the HCl will have a lower pH and the ethanoic acid will have a higher pH, because one's a strong, one's a weak acid. But it's perfectly plausible to have a strong acid which is so dilute, its pH isn't that low. And you could have a weak acid which is so concentrated that its pH is much lower than a strong acid solution. So don't rely on pH being an indicator of strong or weak acids. What you must appreciate is if you've got concentrated weak acids, they can still have a very low pH. And if you've got dilute, strong acids, they could have a higher pH. So the pH, yes, it indicates the level of H+ in terms of concentration, but don't let it be the indication of whether something is strong or weak. You need to look at the acid and decide if it's going to have complete dissociation or part dissociation, but also the Ka values. The bigger the Ka, the stronger the acid. Bigger Ka means a smaller pKa, also reflecting a stronger acid. I hope this is making sense. Let's look at some examples. So here HCl, if I have a 0.1 moles per decimeter cube solution, my assumption that all of this is dissociated into H+ and Cl-, the H+ did not come from H2O in any way, shape or form. Therefore, those two assumptions aside, I can now say that is the concentration of my HCl is also the concentration of my H+, because all of these became H+ and Cl-. So if I have, hypothetically, I'll choose a few numbers here. If I had 1,000 of these in a decimeter cubed, all of them would have split up, giving me 1,000 of these in the decimeter cubed and 1,000 of those in the decimeter cubed. I hope that analogy made sense. The concentration of HCl is the same as the concentration of H+, in this case. It's a 1-to-1 ratio. All of these dissociated, and likewise here. The concentration of my nitric acid here dissociates into these two, so the concentration of nitric acid is also the concentration of H+. What I'd like you to have a go at The first one I've done for you, the pH of this particular solution would have been minus log to the base 10 of my H plus concentration, 0.1. Again, why? Because 0.1 is the concentration of HCl, so it's also the concentration of H plus. That gives me a pH of 1. Try this calculation for yourself. Pause the video here. I'll give you a few seconds. And so my answers for the nitric acid solution of 2.5 times 10 to the minus 5 moles per decimeter cubed, 1-to-1 ratio, that's also the concentration of H plus ions. I put that number into here, minus log to the base 10 of it, gives me a pH of 4.6 to 1 decimal place. So now let's focus on this methanoic acid underneath. 1.5 moles per decimeter cubed is the concentration. We know it's a weak acid, so it partially dissociates. The concentration of these two, the anion methanoate and the H plus, is not going to be the same as the methanoic acid. It's going to be significantly less because of the partial dissociation. But I hope you also appreciate they're going to be equally concentrated, both of these, because every one of these methanoic acids split into one methanoate and one H plus. Let's look further into this. To get the pH, I need to know the H plus concentration. Here is the expression for Ka for methanoic acid, my H plus concentration in the products. Methanoate ion concentration in the products divided by the concentration of my reactant, in this case it was the methanoic acid. That, knowing the Ka, 1.8 times 10 to the minus 4, and I've given you that value here, 1.8 times 10 to the minus 4, we can have a look at this expression now, where the Ka is equal to that. We know the concentration of our methanoic acid. We also know the H plus and the methanoate ions have the same concentration. Let me quickly explain down here. If I had 1,000 of these methanoic acids floating in this beaker, 10 of them were going to dissociate. What I hope you appreciate is if 10 of these methanoic acids were to split, I would end up with 10 methanoate ions and 10 H pluses floating in that beaker, that 1 decimeter cubed. So, what I'm trying to say is if we know the concentration of our acid, we can appreciate whatever is dissociating would have an equal ratio of the H pluses to methanoate ions. Their concentration would be the same. Therefore, let's come back over here. If the concentration of H plus and methanoate ions is the same, that can be simplified to H plus squared, because you're multiplying by itself. This simplifies our calculation to just a single unknown, the H plus concentration. So now the 1.5 can come over. Ka times by the concentration of the acid is H plus concentration squared. The squared can now come over and become square root of the Ka times Ha, or the weak acid concentration, giving me the H plus concentration, which comes out to this number, minus log to the base 10 of that number. The H plus concentration gives me the pH 3.6 to 1 decimal place. I hope this made sense. The Q&A video has a variety of examples that would allow you to perfect your technique and allow you to apply the knowledge you've learned here in this calculation. Calculation can become a bit more awkward, and I'll show you a variety of examples in those Q&A videos. Let's move on to bases. Now for a base, reminding ourselves Bronsted-Lowry base is effectively a proton acceptor. For a base, our calculations that would give us a number above 7 are done in the following way. We already know for pH we do minus log to the base 10 of H plus concentration. We saw that just now. pH is also 14 minus POH. POH being minus log to the base 10 of the OH minus ion concentration. That's another alternative method of calculation I'll show you in just a moment. I've shown the formula here. I'd like to introduce Kw, the ionic product of water. If you're asked to write the definition of this, you can simply write down this equation here. Kw is equal to H plus times OH minus. Now, let's take a step back. Water does very slightly dissociate into H plus and OH minus ions. They have a concentration of 1 times 10 to the minus 7 moles per decimeter cubed. That then gives us a Ka expression of H plus concentration times OH minus concentration all over water's concentration. Now water is effectively a constant. So we can take this constant up and multiply it by this constant. remember this Ka value is a reflection of how much dissociation is occurring. That dissociation is constant at a given temperature and pressure. So if you multiply two constants together, you end up with another constant, and we're calling that the ionic product of water, Kw. This Kw is those two multiplied together. If I multiply this value, which is the concentration of that and that, the value 1 times 10 to the minus 7 multiplied by itself gives me 1 times 10 to the minus 14 moles squared dm to the minus 6. Careful of those units. I'm multiplying 2 moles per decimeter cubed together. I get moles squared dm to the minus 6. Now, this is extremely important for our pH calculations when we're dealing with a base. Let's have a look how. Sodium hydroxide, a strong base, which therefore means it completely dissociates into its ions. Here are those ions. Every one of those forms one of those and one of those. So if that's the concentration of my sodium hydroxide, it is also the concentration of the sodium ions. It is also the concentration of the hydroxide ions. So Kw, the expression here, 1 times 10 to the minus 14 at room temperature and pressure is equal to H plus, we don't know what that is, multiplied by the concentration of hydroxide ions, 0.1. Remind ourselves why, because that's the concentration of the base, so it's the concentration of the hydroxide ion. This, we can look down this calculation first, take the 0.1 round to the other side, it divides. Dividing those two gives me the H plus concentration as shown here, minus log to the base 10 of the H plus concentration pH 13. No surprise that sodium hydroxide is an alkali. It's going to have a pH higher than 7. Fine, seems okay so far. Let's try the alternative method using POH is equal to minus log to the base 10 OH minus concentration. I calculate the POH using the hydroxide ion concentration. That's the number over there. Gives me 1. pH is 14 minus POH. So 14 minus my POH I've calculated here gives me 13. Either method will give you the same answer. Whichever one works for you, keep in mind the examiner may specifically say using Kw, show me. And therefore you would have to stick to this particular method of calculating pH. Again, there's more examples in the Q&A video. Do go through those and perfect your technique. So now turning your attention to some more pH calculations. I've left all the formulae on the page for you. pH is minus log to the base 10 of H plus. pH is 14 minus POH. Kw expression is shown there with its value in units for room temperature and pressure. Keep in mind the reverse of the pH calculation to gather what the H plus is 10 to the minus pH. Take this over to that side. The minus goes over first, minus pH. Log to the base 10 to the other side gives you 10 to the power of whatever's over there. 10 to the minus pH is equal to H plus concentration. These formulae are extremely important for the exam. Let's start by looking at a solution of HCl found to have a pH of 3.5. What's the concentration of HCl? So H plus concentration, let's figure that out first. 10 to the minus pH. There's our pH, so put that number in. This is the concentration of H plus. HCl is a strong acid. So all the H pluses, the concentration of that in the solution is equivalent to the concentration of the HCl's. Each one of those represents each one of these. Therefore, the concentration of my H plus is also the concentration of my HCl. I hope that made sense. If I had, for instance, a base, that's a strong base, KOH, pH was found to be 13.2. Let's put it back into the minus log to the base 10 H plus. Well, 10 to the minus pH, 10 to the minus 13.2 gives me my H plus concentration. Here's my Kw. Therefore, Kw is equal to the H plus concentration times hydroxide ion concentration. That's our unknown. Let's remove this and take it to the other side. That divided by that gives me OH minus concentration, which is this value here. Again, it's a strong base. That is also the concentration of my sodium hydroxide. One of those represents one of those as well. Therefore, my concentration for sodium hydroxide is going to be the same as hydroxide ion concentration to 3 decimal places in this case. And looking further, if I have a solution of a weak acid, methanoic acid, that's the pH. They've given you the Ka. You cannot do the calculation without the Ka. 10 to the minus pH, 10 to the minus 3.5. I now have my H plus concentration. There's my methanoic acid dissociation. There's the Ka expression for this. That can be simplified to H plus squared. The earlier parts of the video to understand why. I have the value for my Ka. I have the value for my H plus. I can put those in and take this to the other side. H plus concentration, which is 3.16 times 10 to the minus 4 squared, then divided by the Ka will give me the acid concentration. So in this case comes to this value here, 5.56 times 10 to the minus 4 moles per decimeter cubed to 2 decimal places. Do keep an eye out for the Q&A video and try to practice as many of these as you can.
Tuition Uncovered. Investing for your future.